Can we turn the lights here?
This. Is it better for you? This light. That's not. Not for you, not for.
The future is here.
Oh yes. Yes. Okay.
Okay. Okay, so let's start our first week of the Brazilian ICPC School 2020. My name is Artem. I was an active competitor about 4 or 5 years ago, and my main accomplishments is I am an ICPC World Champion 2015. And in 2014, we got 9th place and the bronze medal. So I was here as an instructor 4 years ago. Is there anybody who was here 4 years ago, I wonder? Wow. So there will be different topics than 4 years ago, and I try to choose topics in such a way that they don't intersect with previous years or and will be interesting and useful for your competitions. So first, let me tell you about what to use for contest preparations. So first of all, we will use Codeforces platform. I'm sure most of you know about it. It's codeforces.com. We'll hold our contest there, and we'll somehow distribute the invite link to the group with all the contests. And the contest will be there. You can solve them during the 5 hours, and you can then upsolve the problems after the contest. So I hope it's convenient for you to use. There are also a lot more different programming competitions platforms, which are at coder.jp. I'm not sure the time is convenient for Latin America to participate. I think contests will usually begin 9 a.m. local time. So usually most of the contests start on Saturday or Sunday on 9 a.m. local time. Not too bad. Can be worse. There is also an Open Cup, which is worse for you to participate. So Open Cup is a collection of weekly contests. Well, at most weekly contests. Sometimes there are breaks, especially following some larger camps, which is Petrozavodsk camp. Has anybody been to Petrozavodsk camp or an event on Moscow workshops, held by Moscow workshops, I wonder? Okay. So these are large camps, also targeted to prepare for World Finals. And Open Cups are large-scale contests. A lot of participants of Open Cups are not active ICPC participants, so maybe they participated 5, 10 years ago. So a lot of veteran participants, and they usually start at 11 or 12 a.m. Moscow time, which is 6 hours time difference from here, so it will be 5 or 6 a.m. right here. But sometimes it's possible to participate in the contest virtually on the day before. So for you, this will be on Saturday, during the Saturday. There are some logistics that are required to participate in Open Cup. So not everybody can easily get a login, but we'll talk about it later during this week. And of course, there are a lot more. There is Topcoder, which is I think the oldest. There are a lot of online judges that have the problems but don't hold regular contests and so on. Okay. So this week, we will hold 5 lectures and 5 contests. Some contests will be topical. So for example, I tell you 3 or 2 lectures, and then you will solve the compilation of problems on that topics. And some of the contests will be just some contests from past, which I think are good for solving them. So, which I think hold a lot of interesting ideas or interesting problems and will be beneficial for you. So today, we will have an introductory lecture on flows. So a lot of you might know flows. I will try to go in detail. So from basic flows to mean cost flows with potentials and maybe a Hungarian algorithm if we have enough time. So I hope, since a lot of you know flows in some way or another, I hope that, and maybe some of you don't. So I hope a lot of you will learn something new for yourself. And today's contest will be just a usual ICPC contest held almost 5 years ago. And okay, so let's start. So we'll start with flows. So what is a flow? Flows are usually used for solving some kind of transportation problem. So you have some stations and you have some pipes between them, and you can transfer some kind of liquid from one station to another. So there are some pipes. And each pipe has a capacity. So for example, this pipe only can transfer 5 units of water per second. This pipe can transfer 3 units, and so on. Well, most of you are world finals level participants, so I'll just say that we have a directed graph. Undirected graphs also work. We can just count that if we have an undirected edge between 2 vertices, we just make 2 edges. If this has capacity C, then we have 2 edges, C here and C in the back direction. So we will just assume that we'll always have a directed graph in case we'll solve flow problems. So there are edges, and each edge has a capacity. So we'll just say that we have a function So, and 0, I guess. So, for each pair of vertices, we know the maximum capacity. We can say that we have edges, and each edge has a capacity. This is good in case we have a sparse graph. But in general, we'll just talk that we have a capacity function, C of U and V. Is a capacity, is the maximum number of units per second of some liquid or some, or you can imagine that it's a road and the number of lanes is the maximum number of units we can transfer per day or per hour. So the capacity from U to V. Okay, so each edge has a capacity. So we have a directed graph and we have one more function. What is a flow? A flow, we'll call function f. Again, for each pair of vertices, this will tell us some integer number. Flow can be negative, and we'll see why it's useful. So there are 3 properties. So first of all, we have this capacity constraints. So flow for each edge must be less than or equal to the capacity of that edge. So for all U and V, F of U and V is less than or equal to C of U and V. Right, so there are capacity constraints, and for each edge, the flow along this edge. So for example, for this edge, we can maybe put 4 units of liquid along this edge. Can it be 6? And it can be negative. And negative flow corresponds to liquid basically going against this direction. So, for example, if we have 5 units of flow from U to V, it's basically the same as minus 5 units going from V to U. This is why we say that the flow is antisymmetric. So F of U and V is minus F of V and U. Okay, so one more property is, well, usually we have some production center and the consumption center. So usually when we try to deliver water from some source, S source, to some other vertex called T, which we'll call a sink. Usually we produce some amount of water in source and we try to deliver it to sink. And usually the problem is to find the maximum amount of water that we can deliver using these constraints and using these pipes that have limited capacity. So water should not stay at any intermediate vertex, right? So if 8 units of water comes to this edge, there must be exactly 8 units of water coming out of this. So, but it's not true for S and T, right? So it's not true for the starting vertex and it's not true for the end vertex. So we'll say that for every U, for every vertex in the graph that's not S or T, well, this is usually stated as sum of incoming flows is equal to sum of outgoing flows. But since we have this asymmetric property, we can just say that sum of all incoming flows, positive or negative, is 0. Or it's the same as sum of all outgoing flows. So sum over V, f of u and v is 0. It's not true for S, since from source it can go, we can produce some amount of liquid, so the outgoing flow is larger. In fact, the size of the flow is defined as sum of all outgoing flows from the starting vertex of S and V. So we have our S, and all outgoing flow of that is called the size of the flow, or the value. This will usually be the value that we would like to maximize. So F, maximize F. So this is the formal definition of the finding the maximum flow problem. So we would like to find, for each edge, we would like to find some value f of u and v, such that they are antisymmetric, and sum of all outgoing flows for each vertex is 0, so none of the liquid stays at this vertex. And we would like to maximize the flow that we get from S to T. You can notice that it's the same as sum of all V, F of V to T. It's not that trivial, but basically how much liquid goes out of S doesn't stay anywhere in all intermediate vertices, and then adds it T. So if the value or the size of the flow is 0, this means that we don't have a dedicated S or T. Right? So basically, the third rule holds not just for all U that are not S or T, but it holds for S and T. Right? So since this is 0, this is 0, so we can take U equal to S and T, and the third rule will also be true. It doesn't mean, by the way, that flow along all edges is 0. Right? So for example, we'll do it like this. So for each edge, we'll denote F/C. So F is the actual flow, and C is the maximum capacity. So for example, in this, 1 out of 2, 1 out of 1, 1 out of 3. So this is a flow that has value 0, right? So incoming flow is equal to outgoing flow for each possible vertex. This is called the circulation. So a flow with value 0 is called the circulation. This means we'll prove later that every flow can be represented as a union of paths and cycles. So in case the flow is 0, the circulation will correspond to the union of cycles. So for example, there is one cycle, there can be some another cycle, 2 out of 3, 2 out of 4, 2 out of 2, and maybe some edge goes into 2 cycles. So for example, maybe there is another cycle, 2 out of 2 here, 4 out of 4 here, and 2 out of 2 here. So this edge belongs to 2 cycles, basically. Okay, and the problem is usually find the maximum flow. So find these values f of u and v such that the value of flow is maximum possible, such that we transport the maximum number of units from source to sink. So if you are familiar with linear programming, this is a linear programming formulation. Right? So we have some linear constraints. So some value is less than or equal to some constant. So sum of opposite values is equal to 0. And sum values for some of flows along some edges is 0. So this can be viewed as a linear programming. You can plug it into your favorite linear programming solver and you can solve it. This way, you can extend flow problem to, for example, having multiple flows. So for example, you have two types of liquid. You can use one edge for different liquids, but well, you can use, for example, for water and for oil, you can use the same pipes. Don't do that in real life, but let's assume that you can. And there are some constraints on how you can transform. There are no easy algorithms. This is called the multi-commodity flow. And there are no easy algorithms to solve this problem except for linear programming. Well, there are algorithms, but they are quite complicated. And this linear programming formulation is, well, can be generalized for more complicated constraints and for more complicated problems. Okay. Oh, can I go here? Okay. So let's try to solve the maximum flow problem. So the maximum flow problem, find such function f where the value of flow is maximized, where we transport the maximum amount of units from the source to sink. So in flow theory, our graphs are usually called networks. So instead of calling this a graph, we'll call this a network. And there is one more definition that's important, which is called the residual network. So suppose that we have some f is a correct valid flow in G. So all these three rules are satisfied. So if we have a valid flow in G, then we can construct a residual network GF. Now, its structure is the same, but some capacities are a little bit different. So for every U and V, the new capacity, let's call it C prime, with capacities so C prime of U and V is equal to, well, basically residual network means the capacities are what's left capacity. So we have some initial capacity, we have some flow already, and what's left to push along this edge is called the residual capacity. So C of U and V is C. C prime of U and V is C of U and V minus F of U and V. Please notice that in this residual network, even if we didn't have an edge, so for example, if we have an edge that has 2 units of flow going, and it was a directed edge, so we could only push 3 capacity from first vertex to the second one. How does the residual network look like? So it's G and F. What's G? sub f. Well, we still have one unit of flow to push along this edge from left to right. But what happens with the other direction? Well, for the other direction, let's call it u, let's call it v. So for the other direction, C prime of u and v is 1, and C prime of v and u. Well, let's refer to this definition, right? So it's initial capacity, which is 0. There was no edge from u to v in the initial network. 0 minus the flow from v to u. What is the flow from v to u? Well, there was flow from u to v is equal to 2, so the flow from v to u is equal to minus 2. Remember that the flow is asymmetric. 0 minus minus 2, which is 2. Surprisingly, we get this reverse edge from v to u that has capacity 2. What does it mean that we got a new edge that wasn't in the input? This basically means that we can cancel this flow. So we have 2 units of flow going from u to v. And if we push 2 units of flow from v to u, these basically cancel out. Right? So if we have something going like this, so 2 units of flow go here, and also 2 units of flow going somewhere like this. Basically, we can cancel this out. And instead, redirect the flow like this. So 2 units of flow go here and then go here. And these 2 units of flow go into the right vertex and exit out of it. So basically, whenever we have 2 units of flow going in different direction, we can cancel them out. So for each edge, we can only consider that the flow either goes from u to v or from v to u. Okay, now for the most important theorem in flow theory, which is Ford and Fulkerson theorem. Can I go somewhere? I'll only use these 2 whiteboards since this is probably not visible for the people in the far half. Okay, so Ford and Fulkerson theorem tells us that these 3 statements are equivalent. So assume that we have a network. So first, we have a flow and f is maximum. That's not too bad. Second is there is no path in residual network. So assume that we have this residual network and we can still find the path from source to sink. Basically, we can increase. So if we consider GF, so if we have some path along non-saturated edges, so the non-saturated edges are those that have that have positive capacity. So we'll call an edge saturated if C of U and V is greater than 0. Unsaturated. And where the flow is equal to the capacity, we'll call that saturated. So this means that we cannot push more flow along that edge. So suppose that we can find an unsaturated path from S to T. So along all these edges, the residual capacity is not zero. So what can we do with our flow? Well, turns out that we can just increase the flow. We can find the minimum residual capacity. So for example, here it's 2. And for all other edges, it's 2 or greater. That we can increase flow for all these edges by 2. We can decrease flow for all reversed edges by 2. And this will be still a correct flow that has capacity, that the value of that flow is increased by 2. Right? So let's check that all 3 rules of flows are satisfied. So we increased the value along this edge. This means that we decrease the value along the reverse edge. For all the intermediate vertices except S and T, it's satisfied. And what was the last one? Yes, so for all intermediate vertices, so all other vertices that are not on this path are the same. So we'll call that a balance. Well, I will not tell you about the prefill push algorithm today, but that algorithm deals with where we have an unbalanced vertices. So some vertices have larger income than outcome or the other way around. So for all intermediate vertices, the balance is the same. So we increase some incoming edge by 2, and we increase some outgoing edge by 2. Basically, the balance is the same as before. Well, and it is 0. For the starting vertex, it's increased by 2, and for the ending vertex, is decreased by 2. Or we can say that some of incoming flows into the last vertex into the sink is increased by 2. There is one more rule, which was the first one. Right? So we have to check that this flow is less than or equal to all the capacities on all the edges. Well, why is that? Well, C prime of U and V was greater than or equal to 2 in all of these cases. For now, let's only consider integer flows. It's also possible to consider non-integer flows, real flows, or rational flows. I'll speak a few words about them, but usually in contest problems we get integer flows. So if all of these capacities are greater than or equal to 2, this means that C of U and V minus F of U and V was greater than or equal to 2. This is the definition of residual capacity. So what if we increase this F by 2? So this will mean that C of U and V minus F U V plus 2 will be greater than or equal to 0. Which will mean that the new flow that we got, increasing all the values along this path by 2, is still a flow. So still satisfies these 3 rules, and the value of flow is increased. So the most basic algorithm, and all the algorithm that we consider today, will consist of finding the path in residual network from S to T. If we can find the path from S to T, then so if we can find the path from S to T, then this flow is not maximum flow. And we will prove that if we cannot find the path from S to T, then this is a maximum flow. It's not easy to prove that, but we will have 3 statements that are equivalent, which are easy, and this will also provide a very useful technique to solving programming competitions. Okay, so f is maximum possible. GF has no path from source to sink. We basically already proved one implication. So if the flow is maximum, then GF has no path. We basically proved it already. But to prove the equivalence, we have to introduce the third statement, and this talk is about cuts. How do I say it? Okay, let's leave it for now. Let's talk about cuts. So this theorem is also called can be also viewed as an equivalence between the maximum flow and the minimum cut. So what is a cut? So cut. Suppose we have some network. A directed one. And we still have two designated vertices. So the first one and the second one. So source and the sink. The cut is separation of all vertices of this network into two parts. So S large is some vertices. It definitely contains S. So we can look at it like this. So this is S large and this is T large. So the cut is a separation of all vertices of this graph into two parts. First one should contain a source, and the second one should contain a sink. So S and something, T contains sink and some other vertices. These two should be disjoint, and their union must be all vertices of the graph. Well, let's say that S is contained in the first set and T is contained in the second set. So this is a cut. Let's call the cost of the cut all the edges that start in the left part and end in the right part. So, for example, we can have this edge. This way, there are three edges that cross the cut. So this edge, and this edge. So the cost of the cut, we'll call it C of S and T. Is the sum of all costs of edges that cross this cut. So sum over all U in the left part, sum over all V in the right part, C of U and V. Please notice that the edges that go from the right part to the left part are not counted. So for example, this edge will not be counted when we calculate the cost of this flow. So this edge, not counted. A lot of problems on programming competitions will concern cuts. So usually you will try to formulate your problem as a min cut problem, so finding the cut of the minimum cost. such that the cost of this cut is minimum possible. And it turns out that the minimum cut problem can be solved with flows. Okay, let's see. So now we are ready to formulate the third statement. There is some cut st, cut s and t, such that the capacity of this flow is equal to the cost of this cut. So these three statements are equivalent. So the fact that we found the maximum flow is equivalent to the fact that there is no path in the residual network for that flow, is equivalent to that we can find the cut in this network, and the capacity of this and the value of this flow, the size of this flow is the same as the cost of this cut. Please notice that I use two different names for this C, right? So when we talk about flows, this C means capacity, and when we talk about cuts, this means cost, right? So whenever we are trying to formulate our problem as a minimum cut problem, we're trying to minimize the total cost of all edges that cross. We can say that we are calculating the total capacity of flow of all edges that go from left to right, but not from right to left. Okay, and it turns out that solving this problem is equivalent to finding the maximum flow. And I think recently most of the maximum flow problems are formulated like this. Find the minimum cut in this network, do it using the maximum flow algorithm. Okay, so let's start proving this theorem. Basically, as I said, we already proved the one. Our plan will be proving 1 implies 2, 2 implies 3, and 3 implies 1. So 1 to 2, 2 to 3, 3 to 1. This will mean that all three statements are equivalent. And it's easier to prove it like this, and without the third statement would be kind of hard. Okay, so 1 to 2 is basically proven, right? So let's assume not 2, not 1. So if GF has a path from S to T, we can find this path. So if a path exists in the residual network, we can add this path to the flow. So F, if we call F prime F plus P, well, the flow is a function, right? So for each edge, we associate some number, and adding two flows is the same as adding two functions. Integer functions for now, but not necessarily. And we already showed that this is a correct flow in G. Is correct flow in G, and the value of F prime is the value of F plus the value of this path. And if we found the path, this means that the value of this path is positive, so we found the maximum flow. Well, we proved that the old flow was not maximum. So this basically proves that not 2 implies not 1. That's the same as 1 implies 2, right? By contradiction. Okay, let's prove 2, 3, and 3, 1. So 2 implies 3. So we know that we have some flow and its residual network doesn't. So we have some flow F. GF has no path from S to T. So, and to prove this implication, we have to find two sets, S large and T large, such that the cost of that cut is the same as the value of this flow. Okay, so remember that we defined the value C of S and T as sum of for all U in the first part, sum of all V's in the second part, C of U and V. Right? Sum of all capacities of all edges that go from the left part to the right part. We can define the same value, but for flow. F of S and T is the same double sum, but of F of U and V. Is it a meaningful sum? What do you think? Well, it turns out that this does not depend on S and T, and is always equal to the value of the flow. Well, why? First, let's consider these two sets. So S contains just the starting vertex, and T contains all other vertices. Well, what is F of S and T? Basically, we separated our graph into two parts. First only contains vertex S, and the second contains all other vertices. And all flows that go from vertex S are counted in this double sum. So right now, it's true, right? So it's true for at least all sets where S only consists of one source and T consists of all other vertices. Well, what if we move one vertex from T to S? So assume that we have some arbitrary set S, we have some arbitrary set T, and we have some vertex that we would like to move from one set to another. How does this F of S and T change? Well, there were all these edges that were counted in F of S and T. So how is this sum changed? Well, this sum is changed by subtracting all the incoming edges into this vertex. But now, let's call it vertex V. So S plus V and T minus V looks like this. So we have this vertex V right now. And now we add all outgoing vertices. Right? So before we counted all these edges, and after we count all these edges. And we know that these two values are the same. Right? So basically we can reverse these edges and add all these edges, and we get all outgoing edges from vertex V. And this means that the value of V of S and T does not change if we move one vertex from another. This means that it's true for all possible cuts. For all possible ways to divide all vertices into two parts, the F of S and T will be the same. Yes, so all edges from the left part to the right part. If we calculate all flows from the left part to the right part, this will be always equal to the value of the flow. Seems kind of meaningless, right? So why do we define some value that is constant no matter what sets S and T are. Well, turns out not that useless. Well, we know that f of u and v is always less than or equal to c of u and v. Right? Well, it turns out that we have these double sums, and each term here is less than or equal than corresponding term here. This means that for all possible sets S and T, f of S and T is less than or equal to C of S and T. Pretty obvious, right? We have these double sums, and each term here is larger than each term here. Well, not each term here, but rather than corresponding term here. Okay, so what does it mean? It means that if we find some S and T where this is equal, where we have an equality here, so f of S and T is equal to C of S and T, what does this mean? It basically means that all edges from S large to T large are saturated. So all edges that go from first part to the second part are saturated. That means that flow is equal to the capacity, so we have double sum where all terms are equal. This means the sums are equal. Okay, so we have, if we find such S and T where the value of flow is the same as the cost of this cut, and this means this is equal to F. Oh, sorry. So, how do we find such S and T where all edges from S to T are saturated? Let's run some graph search algorithm. So we have this residual network, and there is no path from S to T. So run, let's say, DFS S from source. That only goes, well, that only exports the residual network, right? That only explores unsaturated edges in GF. So we cannot reach T. Right? So otherwise there would be a path, and the implication that we're trying to prove tells us that there is no path. Okay, turns out that if we set S to be all reached vertices and T to be all other vertices, then this will be a correct cut, and all edges from first part to the second part will be unsaturated. Let S be reachable vertices. In GF. And T all the other vertices. Right. So T is V minus S. So turns out that the cost of this cut will be the same as the value of the flow. So all edges, so T contains T small, so at least it's not empty. S large contains S small, and by this definition they are disjoint. So this completely satisfies our definition of cut. So all edges S from S to T are saturated. Is this a good size? Should I write smaller or larger? Can you see from the later rows? Okay. So all edges from left part to the right part are saturated. This means that the cost of this cut is the same as the cost of this flow. So we prove the implication, right? So this is basically this is a constructive proof of how to find this cut such that the value of the flow is equal to the cost of this cut. So the total capacity of all edges that goes from left to right. Basically, we try to find the cut where all edges are saturated, and we did it by just looking at all reachable vertices in the residual network. Okay, now for the last implication, this will be easy. So can I erase this? So now we try to prove 3 implies 1. If we know that there is f that's equal to cost of some cut, and we would like to prove that f is maximum. So the fact that our flow is equal to the value of some cut means that this is as large as possible. Okay, it turns out that the value of any flow is less than or equal to the value of any cut. So any flow, so for all possible f flow and st cut, the value of f is less than or equal to the cost of this cut. And if, so for all, this means that if we take the maximum flow and we take the minimum cut, this is still true, right? So all possible flows, if we look at the number line, all possible flows and all possible cuts, every flow lies to the left to every possible cut. But they meet somewhere. This is what 3 tells us, right? This tells us that there is a cut where the size of our flow is equal to the size of this cut. F C of S and T. Well, why is that? So the last thing we have to prove is that any flow is less than or equal to any cut. Well, it's easy. We almost proved it already, because we know that the flow over from one set to another is less than or equal than to size of that cut. So for all possible f, s, and t, we know that flow over s and t is less than or equal to cut of s and t. And we know that this is the value of the flow. So this is constant. So this is independent of S and T. So the value of the flow S and T is constant for any 2 sets S and T, which means that the value of the flow is less than or equal to the cost of the cut from S to T. Okay, So it was a large theoretical introduction. Now we move to algorithms. So since we know that the minimum cut is equal to the maximum flow, and we already know how to constructively find the minimum cut, right? So first we convert it to the maximum flow problem. We solve the maximum flow problem. We find all vertices that are reachable from the source. This will be the left part of the cut, and all the other vertices will be the right part of the cut. And sadly, this is not the easiest part in flow problems. Sorry, I meant to say this is the easiest part of the maximum flow problems. Like implementing the algorithm is the easiest part, and the harder part is how do we transform the problem statement into the minimum cut problem. We will look at a few examples right here, but this field is very large, and there are a lot of interesting techniques on how to create networks such that the minimum cut in this network corresponds to the answer to the problem statement. This is, I would say this is art in itself. Well, what we do with solving competitive programming problems is transforming the problem statement into what we can solve with algorithms, and this is usually the hard part in flow problems. Okay, so let's look at algorithms. The first one is just follows from the Ford-Fulkerson theorem, right? So this tells us that the flow is maximum if and only if there is no path from S to T. And this means that we just can find paths in residual network. We can increase the flow along this path until we have no path. So this is called Ford-Fulkerson algorithm. So start with an empty flow so that the flow along all edges is 0. 0 while exists path in GF. We add F and P. So while there is a path in the residual network, we can add this path to our flow. We already shown that it is a correct flow and its value is increased. So we can do that until we get no path in the residual network. So what's the time complexity of this? Well, the time complexity is, let's say we use DFS for finding a path. So it runs in n plus m. N is the number of vertices, m is the number of edges. Well, in the worst case, well, if we find a path in the residual network, we can just take one. If we have integer capacities, we can just take one unit of flow and push it along this path. Or we can do something smarter and take the minimum residual capacity on this path. So for example, in the example that was here, we found that the minimum capacity was 2, so we can push 2 units of flow along that path. But in the worst case, we will always find the path that has capacity 1, residual capacity 1. So it's times the value of the maximum flow, times the value of Fmax. This, Well, speaking in complexity theory terms, it is not a polynomial algorithm, right? So we can create a small network like this. I don't remember the exact capacities here. Something like this. So this is very large, 10 to the power of 9. This is very large. This is very large. And this is very large. And this is 1. So on this network, you can be unlucky and every path that you find in the residual network will result in adding 1 to your flow. Right? So for example, in the beginning, you can find this path. Okay, minimum residual capacity is 1, so we add 1. So it becomes 1 out of 10 to the power of 9, becomes 1 out of 1 here. This means that there is a back edge minus 1 out of 0, basically. So this means that we can cancel this unit of flow that goes from top to bottom if we push 1 unit of flow from bottom to up. This is also 1 out of 10 to the power of 9. 1 out of 1 billion. And what would we do on the next step? Yes, so we find the symmetric path that goes down, up, and right. Yes. So again, this unit of flow is cancelled. We get 1 out of 1 billion here, 1 out of 1 billion here, and 0 out of 1 here. Of course, we could be smarter and just see that, okay, we push 1 billion here, 1 billion here, 1 billion here, 1 billion here, and we're done. But we can be unlucky if an adversary chooses the path for us each time in this network. In the worst case, if we choose the worst path every time, we can work up to n plus m times the capacity, times the value of the largest flow there is. An improvement to this algorithm is finding not just any path, but let's find the shortest path in terms of the number of edges. This is called an Edmonds-Karp algorithm. And the only change that it uses BFS instead of any other graph search. So you know that BFS finds the shortest path in terms of the number of edges. So if we find the shortest path, then we choose the minimum and we choose the minimum residual capacity on that path. Then we push that number of units of flow along that path. Turns out that we always finish in polynomial time. I'll prove it without a lot of details, but if we have some path from S to T, at least since we use the minimum residual capacity, at least one edge becomes saturated. So let's say that we have this edge that becomes saturated. Okay, so what happens when it becomes saturated? Well, basically it gets removed from this graph and we get the reverse edge in the residual network. Well, it turns out, since we're using BFS, so we're finding shortest path from search to all other vertices, that the shortest distance, let's call this U, and let's call this V. The shortest distance to U is increased. So we know, since this was the shortest path, we knew that distance of v is equal to distance to u plus 1, since this was the shortest path. Turns out there will be no other path to u that uses this edge. So whenever we find a path, at least one edge is reversed. And each edge can reverse well, how many times? Each time an edge is reversed, the distance to its beginning is increased. And the distance can be larger than the number of vertices. So each edge can reverse v times at most. So the total number of all edge reversals is O of v times e. And we find the shortest path in, let me use n and m still. So n times m times m plus n. So this is the total, n times m is the total number of reversals of all edges, and the m plus n is the runtime of BFS. This is BFS. So we get, usually the number of edges is larger than the number of vertices, of course, so this is n m squared. In practice, there is a network where this algorithm works about this time, up to some constant. But in reality, your networks are specialized, right? So you created this network for this problem. So you used these costs for production, and you use this cost for consumption, and so on. In reality, this is faster than m squared. But the last algorithm that I will tell you before the break is Dinit's algorithm. And first of all, it's a lot faster than just finding the shortest path. And in practice, it works really well. So in practice, you can run Dinit's algorithm on networks up to, I don't know, 100,000 vertices. And maybe you can expect a success. Not always, but thank you. If you don't have anything to do, this might be a correct course to proceed. Okay, so Dinit's algorithm can basically be described in like 5 lines of code. While there is a path, S to T. Well, what did we do in Edmonds-Karp algorithm? So each time we found the shortest path from source to sink, and we push the flow along this path, and then recalculate all shortest paths again. Turns out that we don't need to find all shortest paths again, and we can do it like this. So we can run BFS in the residual network and save all shortest paths. save all distances, let's say. So let's say we have array dist of u. Okay, so now we'll create a layered graph. So we have S here. This will be level 0. The next level, the next layer will be all vertices that are reachable from S in one step that have distance equal to 1. The next layer will be the next step, and so on. There are other edges, right? So there are edges inside one layer, and there are edges from later layers to the former ones. We will not care about those edges at all. So we will only consider edges to only consider edges u, v, where the distance to vertex u plus 1 is distance to vertex v. And we'll try to find the flow only using those edges. So suppose we can find the flow that only uses those edges, such that there is no more path from S to T along those edges. What does it mean? This means that the distance from vertex S to vertex T will increase. And this can happen in residual network at most n times, right? So in the beginning, the distance will be at most 2. Then on the next step, this will increase by 1, by 1, by 1, by 1. We'll call it a phase. So the Dennis algorithm will contain at most n phases. Now, our problem will be to, using this specific structure of the network, find the flow. It's also called the blocking flow, where there is no edge, there is no path from S to T that only uses those edges. Maybe there is maybe there is a path that uses this kind of edge. So for example, we can go like this. And now maybe there is some other vertex. So maybe we can find a path that goes like this. But we will not care about those paths. We'll only find the blocking flow that only goes from left to right. And since there is no path from S to T, the distance in the residual network will necessarily increase. And it's enough to guarantee the linear number of phases. For find blocking flow. And we'll see how to do that in n times m time. So there will be n phases at most. And each phase will be solved in m times n time per phase. Of course, it's an upper bound every time. So in total, our algorithm will work in n squared times m. In reality, it's a lot faster. So there are two theorems that if we have, for example, unit capacities, there will be not n phases, but square root of e phases, square root of m phases. And if capacities are not unit, but are small enough, this will still work pretty fast. Okay, so while there is a path, find all distances, find blocking path, blocking flow, sorry. Okay. So how do we find the blocking flow? Well, let's try and just run the DFS. So we go from S, we see some unsaturated edge, we go along this edge, we see some unsaturated edge, we go along this edge, and so on until we reach T. Then we found some path, we increase the flow along this path, and then try again. So basically, the second part is while there is a path in this blocking network, in this layered network, while DFS finds a path in blocking network, let's say in this layered network, add it to flow. Yeah. So for now, this doesn't work quickly. But if we make some observations, then this will become a fast algorithm. Let me just write a pseudocode for the Dennis algorithm, or at least how I do the implementation of this algorithm. Okay, so first of all, I need a structure for an edge. Right? So, by the way, a quick survey. Who of you does not use C++ for programming contests? Any of you? Everybody uses C++? Okay. That's good for you. Not so good for me since I'm used to Java. And okay. So first of all, we need some structure to store edges, right? So edge. Well, what do we need? What does edge need to know? Well, the edge need to know is where it's leading. So let's call it int2. It needs to know its capacity. Let's call it cap. And it needs to know what's the current flow. Well, maybe the flow is long and capacity is long. Well, what more? Well, since we're storing not just an adjacency matrix of the graph, like what I was using C of U and V, in theory, is good in theory, but it's worse for the practical implementation. So usually we want to do better for sparse graphs. So we'd like to know what is the reverse edge. Adding a flow along this edge also means decreasing the flow along the reverse edge, since those are antisymmetric. So to increase the flow along this edge, we also need to decrease the flow along the reverse edge. So we need to somehow know the reverse edge. We can store a pointer. So that's what I did in Java. Or you can use indices for all edges. So just imagine that in the beginning, when you constructed your network, you created a long list of all edges. And the two edges, the forward edge and the corresponding backward edge, were neighbors. So for example, at 0, we have this edge, and on 1, we have the reverse edge. So now we'll have to deal with edges as just integers. Then to change any properties of these edges, we'll have to access this array. And to find the reverse edge, we just use index XOR 1. Right? So if the number was even, we get the corresponding odd number. If the number was odd, we get the corresponding even number. Okay, so let me use this. I'm more used to it. And I think a lot of you have implemented this already. And you will implement it tomorrow. So let me describe it like this. And if you'd like to use XOR 1 technique to access the reverse edge, it's up to you. Okay, and that's basically it, right? So we don't do we need anything more from this edge? Okay, so that's it. That's all we need to know from this edge. For each edge, we know the capacity of flow, and we don't even need to know the starting vertex. We only need to know where this edge leads to. And I'll store the graph as an adjacency list. So a vector of let's say the vector of edges graph. And so I'll use array of vectors or vector of vectors. Let me use vector of vectors. Okay. So the BFS algorithm is standard, right? So you have a queue, you push the starting vertex into the queue, you only follow unsaturated edges, and you find the shortest distances. So the BFS algorithm is standard, but the DFS algorithm here is not. So I want my DFS to return what is the number of units of flow that this DFS actually pushed through. So I'll use int DFS. Well, I started at some vertex. I want my DFS to update the flows on the go. So I don't want to find the path, then go through all edges of this path and increase the flow. So I want to use, I want to pass as an argument one more thing, which is what was the minimum capacity so far? So what was the minimum residual capacity so far? So int u, this is the current vertex, and int, let's say flow. What was the minimum capacity so far? So we got from S to this vertex u. Now we'll consider all outgoing edges and try to run DFS from all those vertices. Okay, so first of all, if we reach the end, then we just return this flow. So if u is equal to t, then we just return flow. So if we reach the end, so if we've come to the vertex t, and we know that the minimum capacity so far was flow, then we can push this number of units of flow along this path. Now, we try all possible outgoing edges. Let me just say it like this. For edge E of the graph of U. Now we need to check whether we will only use edges that go from previous layer to the next layer. So if dist of E2 is dist of U plus 1, and there is one more thing, that this edge has to be unsaturated. And well, what does mean that the edge is unsaturated? This means that the flow is less than the capacity. E flow less than E cap. In this way, we run the DFS. We see what it returned. And returned is DFS of E2. So the next vertex is E dot 2. And the minimum capacity is minimum of what was there before and this new residual capacity. So min of flow and E cap minus E dot flow. So the previous minimum residual capacity and the new one. And the minimum of those two is the new minimum. Okay, so if we return something, there will be two variations of this algorithm. Let me just explain the first one that's easier to explain, and the second one that's better to implement will be the next one. So if we return something, then we add the flow to this edge. We subtract the flow from the reverse edge. We should always do that in all possible flow algorithms. So it's E dot flow, add this returned value, E reverse dot flow, we will subtract this. And let's just say that we return it. So as long as we found the path, so we go here, maybe we'll go somewhere else. If we find the path in the residual network, we just add it. So we return red. Okay, so for now, this version of algorithm is slow. So and there's one more thing. If we haven't returned anything, then we should return 0. Right? So if we look if we've come to the vertex U, we tried all possible outgoing edges, and none of them could find the path to the end vertex, then we just return 0, right? So we can push 0 flow. This means, okay, return 0. Okay, so that's it for now. And this is still slow. Let's make one more observation that will make this algorithm work in n times m. Turns out, well, let's look at some edge. So we see that this edge from U to V. So we've come from S to U somehow. And then from V, there is no path to the end vertex. So there is no path to vertex T. Basically, whenever we made the recursive call and it returned 0, this means that we will never be able to use this edge again. Right? Because in this layered network, there are no new edges. Right? So the only edges that have their capacity, the residual capacity increased, are the back edges. Right? So the edges that go from former layers to ladder. So the other way around, right? From ladder layers to former layers. So if we haven't found the path from this vertex V to T, then we don't need this edge. We can remove this edge. Basically here, if we return 0, then we just remove this edge. Here, if red is 0, remove edge E. We will never need it again on this phase. Right? So we might need it later on the next phase, but on this phase, this edge is useless. Right? So if we run from this vertex and haven't found the path, we don't need this edge. Let's consider some other vertex. So you might notice that we don't use any marks for vertices. So we can visit some vertex more than once. But if we visited some vertex and we returned 0, and we came to this vertex again, this means that there are no more outgoing edges from this vertex. So if we run DFS from some vertex and the recursive call for this vertex returns 0, this means that all outgoing edges are removed. This means that each return value here was 0, and there are no more outgoing edges. And when we come to this vertex the second time, we just return 0 immediately. So there are no problems that we can visit the same vertex multiple times. If we visit the vertex for the second time, we will just return immediately. So, well, removing an edge from the list is an expensive operation, right? So removing an edge from somewhere so we don't use it later is kind of expensive. But let's see what happens in this algorithm. So there are some edges from vertex U. So there's the first one, second one, third one, fourth one. So we've come to vertex U. We use the first edge. So if it returns something, then great. We increase the flow here, plus flow. and return it back, and we can use this edge maybe again. So maybe there are 2 more paths going out of this. Maybe there are several paths that go out of this vertex to the end one. But, so for each edge, we use it, until we get 0, then we remove it. Then, for each vertex, we use the second edge some number of times, then we remove the second edge. So we'll always remove some prefix of these edges. So instead of actually removing edges, let's just store a pointer to the first non-removed edge. Let's call it start. Int vector int start. That will tell us for each vertex what is the index of the first edge that we haven't removed yet. First non-removed edge. Okay? So this would look like, instead of iterating over all edges, we will just iterating the start variable. We'll check the first non-removed edge. Maybe we can use it again. Then we don't increment start. So this will look like this. This for loop will look like this. So we don't have any initial conditions. The start of vertex u should be less than graph of u dot size. And we start of u increase it every time. And here we say that edge E let's say edge E is graph of u and start of u. Now, let's see how this optimization makes this algorithm work in big O of n times m. Well, an obvious point that there are less than or equal than m paths. So this algorithm DFS will run at most, will find at most m paths in total. Well, why? Because each path makes some edge 0. And each path will be found not in each path will be found in linear time in the number of vertices. So if you remember, DFS or BFS will find a path in n plus m time, but here each path will be found in n time, right? Because, well, there are n layers, and we either go to the next layer or we remove an edge. So each operation either advances us to the next level, to the next layer, or removes an edge. So we have to count 2 different types of operations. Actually finding paths, we find m paths and the total length of each path is at most n. So the total length of all paths that we find is big O of n times m. And Whenever we don't find a path, we remove an edge. And the total time it takes to look through all useless edges is linear in the number of edges. So the total, this algorithm takes n times m time. And this is small pseudocode reference implementation of how I do this algorithm. There is one more optimization that I want to tell you, is we don't have to return each time we find some path. Right now, we start from source, we find some path to T, we go all the way back to S and increase all flows along that path. Instead of, so if we find some vertex, let's say I have some vertex, what's the name? Vertex P here. And there is an outgoing edge that we can use to push more flow through this edge. Let's not return from this vertex P immediately, but instead I'll try to explore this edge once again. Okay, maybe there is another path. Well, I cannot use this edge once again, but I can use more edges out of this vertex again. So the way to do that is to not return every time you found the path, but instead you can reuse the same vertex more than once in each path. And it's slightly faster, but asymptotically it's the same. Okay, so what's the time our lecture ends? In an hour, right? Okay, so now let's make a small break for 10 minutes and we will continue with the short stories about flows with costs. Or, well, let me think about it. So we have 45 minutes left until the end. So I think I'll dedicate those 45 minutes to example of problems that can be solved with maximum flow or can be reduced to minimum cut. And we'll leave minimum cost flow for another day. Is that okay? Can anybody ask everybody to return? So I decided that we use the remaining 45 minutes to discuss how to solve problems and how to reduce different problems to min-cut problem. And the next day we'll dedicate fully to min-cost flows and Hungarian algorithm. Okay, so the first use that I think, if you know flows, you know that this is the example, is bipartite matching. So you have a bipartite graph, and you want to find the set of edges such that all vertices in the left part are different and all vertices in the right part are different. And as usual, you'd like to find the matching of the maximum size. Well, how do we solve this problem with flows? Let's create an artificial source, and let's create an additional sink. Let's draw all the edges to all vertices in the left part from the sink, from the source, sorry. All these have capacity 1. All the edges from, let's draw all the edges from the right part to the sink. They also have capacity 1. And these edges doesn't matter. You can make them infinite capacity. You can make them capacity like very large. You can make capacity 1. Doesn't matter. Okay, so when we find the maximum flow in this graph, let's look at all saturated edges. I claim that maximum matching is saturated edges between left and right part. Let's call this L, let's call this R, L to R. We can also direct all the edges from the left to right. Well, why is data matching? If we look at all the saturated edges between these vertices, why is it a matching? Well, because no two edges can have the same vertex in the left part, since there is only one unit of flow that can go into this vertex, so we can choose at most one edge going out of this vertex to the right part. And the same for the right part, right? There can be two saturated edges that go to the right part, since only one unit of flow can go out of this vertex. So each edge, each vertex on the left and on the right can only have one incident edge. This means that flow corresponds to matching, and we can do the back. We can do the reverse, right? So for each correct matching, we can build a flow. So, and the capacity and the size of matching corresponds to the value of the flow. Size of, let's say, number of edges in maximum matching. Of edges in matching. And so to prove that this maximum flow formulation actually solves the bipartite matching problem, you have to show the bijection between flows and matchings. And you have to show also the correspondence. So the maximum flow corresponds to the maximum matching. Okay, so for the maximum matching problem, there is a Kunz algorithm that works in O of n times m. What happens if I run Ford-Fulkerson algorithm on this graph? Will it have the same time complexity or slower, or maybe even faster? Yes, the same time, since the maximum flow has value at most n, since there are at most n edges in maximum matching, and times big O of n plus m, that's the runtime of one DFS. So Ford-Fulkerson algorithm and Manskar algorithm will always find. But since Kunz algorithm is specialized for bipartite graphs, so there are some optimizations, it usually works faster. The same comparison goes for min cost algorithms and Hungarian algorithm. So these algorithms that are more specialized, they usually have the same time complexity, but the constant in big O is smaller, so it's preferable to use them. I know problems where min cost flow was too slow, but Hungarian algorithm that has the same asymptotic runtime is enough. And of course, when you formulate your problem as the flow problem, you can generalize a bit. So for example, you can make rules such that, well, not every vertex has to have only one edge incident to it. Maybe vertices in the right part can have two edges, right? So to transform this problem into this new rule, such that vertices in the left part must have at most one edge, and vertices in the right part can have 0, 1, or 2. So this is the simple change in the network. Okay. Do you know what a vertex cover in a graph is? Vertex cover is a set of vertices. Vertex cover. A is a subset of vertices such that each edge has either both ends or at least one end belonging to the set A. So the set of vertices such that there is no edge between two vertices outside of this set. Every edge has at least one end in this set A. So, and there is a conic theorem that tells us that the size of the vertex cover in bipartite graph is equal to the size of the maximum matching in this graph. Have you heard about it? And maybe you even know the algorithm how to, given a maximum matching, how do we restore, how do we find the vertex cover in the bipartite graph? There's one simple DFS, and then we find all the other. Turns out, then we can easily find the vertex cover with flows. Turns out that the vertex cover roughly corresponds to what do you think it is? Yes, the vertex cover in this network vertex cover for the initial bipartite graph roughly corresponds to the min cut in this network. Okay, so let's see. Let's find the maximum matching here. Can we have a matching of size 4? So we have to do it like this. Then we have to do it like... Oh, we cannot do it, right? So there is no matching of size 4. And there is of size 3. Right? Right? So let's create a flow that corresponds to this matching. So we have these edges are saturated. This one, and this one, and this one, and this one. So these edges are saturated, and all the other edges are unsaturated. This means, basically this means that the direction of all the saturated edges is reversed, since all edges have unit capacity, and all the other edges are still the same. Let's find the min cut that corresponds to this flow. What do we have to do to find the min cut? Well, we have to find the reachable vertices from here, right? So which vertices are reachable? We can go here. We can go here. We can go here. We cannot go here, but we can go in reverse here. So we can go here. We cannot go anywhere else from this vertex. Now we can go use this edge here. We can go back using this edge. We can go forward using this edge, and so on. So these vertices form S. And all the other vertices form T. So this is T. Right, so this is T. And blue is S. Okay, so let's see. Now, we need to form the maximum. We know that the cost of this cut is equal to the maximum matching. Well, which edges cross the cut? There have to be 3 edges that cross the cut. So there's too much on this picture already. So an edge that crosses the cut is the edge that goes from blue vertex to red vertex, right? So there is this one. There is this one. This one does not cross the cut. Okay. Turns out I forgot one more thing to do this. Well, I told you that we can make these edges as high as we want, right? So in the proof, where each flow corresponds to the matching, so the maximum flow corresponds to the maximum matching, we didn't use the fact that these have capacity 1, right? So we only use that all the vertices that connect S to the left part have capacity 1, and all the vertices on the right part and T also have capacity 1. We didn't use the fact that middle edges have capacity 1 at all, right? Let's make all of them infinite. So instead of 1, Let me redraw this graph. So this goes here. This goes here, here, and here. This goes here and there. This goes here, this goes here. So let's make all these edges infinite. This will change sets S and T a bit. But if we have infinite edges, this means that the cut, none of these infinite edges can cross the cut. So if one of these edges crosses the cut, this means that the cost of the cut would be infinite. But if we cut like this, so S here and everything else, the cost of this cut would be finite. Infinite edges is a common trick to make some restrictions on what your cut looks like. So if you have an infinite edge, you basically tell you cannot make such that the first vertex is in the first set and the second vertex is in the second set. This edge cannot cross the cut, so either these two vertices are in the same set or this. So if you make an infinite edge, you can restrict the possibility where this belongs to S and this belongs to T. You can make this restriction. If you are familiar with the two-sat algorithm, this basically is like this. So the minimum cut problem is similar in some ways to two-sat. Right. So you have basically, for each vertex you have a variable, either it belongs to the left part or to the right part, and then you have cost. What do we pay if this vertex belongs to the left part and this vertex belongs to the right part? This corresponds to an edge. Okay, so we make these vertices infinite. We make these edges infinite, so we can go from left to right, even if this edge was used in a matching. So these sets will look different. Let's see. So what is the matching here? Matching is this, this, and this. So basically we look at three vertices on the left, so those vertices that don't have a matching assigned to them, that are not covered by a matching, and we run the DFS from them. So we can go here, we can go here, we can go here, we can go here, and that's it, right? So all the other vertices are red. So you can notice there is no infinite edge that goes from a blue vertex to a red vertex. Is that correct? And all the edges are from left to right. So there's no blue vertex on the left. So there are blue vertices on the left, but they all lead to blue vertices on the right. Okay. So now, let's see which edges cross the cut. Let's remember that we have a blue vertex S on the left and the red vertex T on the right. So, which edges cross the cut? Well, there is one edge from S to this red vertex, right? So we're trying to count the edges from blue to red. And there are two more edges, this one and this one. So we know that the cost of this cut is 3. So, and these are 3 edges that cross the cut. No edges between the left part and the right part can cross the cut since they are infinite. And only edges are from S to the left part and from the right part to T. Well, I claim that these 3 vertices that have their corresponding edges that are in the cut form a vertex cover. Well, why? Can there be an edge not covered by any of these 3 vertices? Well, in the initial bipartite graph, can there be an infinite edge that's not covered by any of these vertices? Why not? So, assume there is an edge. Well, an edge cannot go from blue to red. So, an edge either goes from red to red, from blue to blue, or from red to blue. There are only 3 possibilities, right? So these edges are infinite, so they cannot go from from blue to red. Okay, so in this case, we took this vertex into the vertex cover, right? So this is a red vertex in the left part, so this edge crosses the cut. So in this case, this vertex is taken into the vertex cover, and this edge is covered by the vertex cover. In this case, this vertex has the edge to T. So this is a blue vertex in the right part. So this edge crosses the cut. This means that we take this vertex into the vertex cover. And in this case, both of these cases are true. So we took both this vertex and this vertex. And this can sometimes happen. So for some edges, the optimal way might be to take both the left part and the right part, because it's better when we have some other edges. You can consider the case some kind of degenerate case. So when you have 3 vertices here, 3 vertices here, you have this edge. You have this kind of bipartite graph. And the only optimal vertex cover is take this and this. You cannot take less than 2 vertices. And it's the only optimal way to take 2 vertices. There is an edge between them, but okay, happens. And let's look at one more, a very common problem. And a lot of problems are reduced to this one, and it's called the closure problem. Okay, I'll be here for a while. So, can I erase this part? Oh, it's back. I'm here. Okay, so we'll talk about the closure problem. Closure problem. And it looks like this. We have a directed graph. And each vertex has a cost. we need to find some subset of vertices such that there is no edge from this subset to the complement of it. So we need to find some closed graph in some sense, such that some part of the graph, such that there is no outgoing edges out of this graph. There can be edges into this graph. That's fine. But there cannot be edges outside of this graph. So all edges leading from vertices in this graph lead to the same vertices in this graph. That's why it's closure, since this is in some sense a closed subgraph. And we need to find the subset with the maximum cost. Find subset S, where if we have a vertex, if U belongs to S, and there is an edge UV, then V belongs to S. So in some sense, a closed subgraph. Maximize the cost of this subset S, where the cost of the subset, of course, is the sum of costs of vertices. So here I expect a question here. Why don't we just take all the vertices? Yes, that's the answer. So sum of costs might be negative. So if all costs are positive, of course, we have to take the whole graph. But some costs might be positive, some costs might be negative, and now the problem has meaning. Okay. So if there were no edges, what would the solution look like? Yes, we'll just take all positive vertices and don't take any negative vertices. Okay, so let's take all positive vertices and then we'll sort out the conflicts. So let's have two sets. A is all vertices where the cost of the vertex is positive. Let's say non-negative. And B, all the vertices that their cost is negative. So let's take A and then maybe remove some vertices from A, or maybe we will add some vertices from B such that the subset is closed. Okay, so for each of that decision, we will have to pay, right? So either for excluding a vertex from A, we'll have to pay its cost, or for including the vertex of B, we'll have to pay the negative of the cost of the vertex we're trying to include. This looks like a minimum cut problem. So for each vertex, we either take it or not take it. And if we include it on the left, in the left part, so if it was positive and we include it, we don't pay any cost. If it was positive and we don't include it, we pay the cost associated with its value. If it was negative and we take it, we pay the cost. If it was negative and we don't take it, we don't pay the cost. So this, without the edge restriction, the network would look like this. So we'll have A first. Then we'll have B second. We have S and T as always. And now we'll draw costs, right? So let's say that set S, so in the end, we'll create cut S and T. And the vertices on the left part will be included in this closed subset. So S without this artificial S is the subset that we take. And T without small t is all other vertices. All other. And we have to maximize the cost of S. Well, as I said, in the beginning, we'll just take all vertices, all positive vertices. This means that we will pay for not including those vertices. So whenever one of these vertices belongs to the second set, we would like to pay the cost. This corresponds to, we'll have this edge with cost C of that vertex. Since if this vertex belongs to the second part, this edge will cross the cut and we'll basically pay for crossing this edge, which corresponds to not including this vertex into this closed subgraph and subtracting the cost of this vertex. And for all the other vertices, what we'll do is draw these edges with cost minus CV. Well, this cost is negative, so minus CV is positive. Usually, when we're trying to formulate the problem as the minimum cut problem, all our costs have to be positive. It's hard to solve minimum cut problem where you can have negative costs. So for example, min cut problem is polynomially solvable. Min cut is in P. But if we invert all costs and make it negative, finding min cut is the same as finding the maximum cut in the problem. And max cut is NP complete. So there is a strong suggestion that we can't solve max cut efficiently yet. So whenever you're trying to reduce your problem to the max cut, you have to make your costs positive. So this way, I cannot just make all the edges here cost CV, because there will be some positive costs and some negative costs, and I cannot do that. So I have to somehow make my weights all positive. Okay. So for now, the max cut, the minimum cut on this network is just this, right? And we don't pay any costs, and our initial first approximation to the result is costs of all positive vertices, and okay, so we take them all and we don't pay any costs, so our result is the sum of all these costs. So what do we have to do now to add the restrictions on edges? So we have edges that if we take some vertex, then we have to take some vertex. So if we take this and there is an edge, if we, let's call this U and V, if we take V and there is an edge from U to V, then we have to take V too. Let's take U, sorry. Then we have to take V. Yes, so we just add this edge, but with infinite capacity or infinite cost. So for example, if we take this vertex, we need to take this vertex too. And if we take this vertex, we take this vertex too. So we add these edges, but with infinite capacity. So now, this is not the best cut, right? Right now, this is not a good cut at all because it crosses an infinite edge. So maybe the max cut looks something like this. Maybe taking these two vertices is worse, including this vertex too. But maybe this vertex costs, well, the profit that this vertex gives is too low. And it would be better if we excluded this vertex but did not include two vertices with negative costs. Well, in general, we have to find the minimum cut in this network. And a lot of problems are reduced to this kind of problem. So we have a directed graph, we have some costs, and we have to find a subset where no edge leads out of this subset, but some edges can go inside of this subset. And the cost is maximum possible. Some vertices are positive, some vertices are negative. So, and there are two, well, these are two most common examples of problems solvable with max flow. You can think about what happens if we're trying to find not just the vertex cover, but the weighted vertex cover. So there is a cost to take each vertex into the max, into our vertex cover, and we're trying to find the minimum weighted vertex cover. Or finding the independent subset, which is the complement of a vertex cover. And there are a lot of problems that are reducible to the closure problem that I described here. So, do you have any questions? Okay, so I think the plan now is tomorrow we'll talk about mean cost flow, mean cost max flow, and the Hungarian algorithm, and all the optimizations that are connected to it. Tomorrow we'll have a contest about flows, so both mean cost flows and normal flows. I'll try to find interesting problems that have interesting reductions to mean cut. And I think that's it. So again, next time, if you have questions during the lecture, please raise your hand and I'll answer your question. I'll try to answer your question immediately. Okay, thank you.
So you can go to that door.
Okay, so I just have some questions for you, more about like what we should study for ICPC. My team's going to ICPC this year, and we are kind of the dream we're aiming for is to get a medal, a low medal, which the team got kind of close to.
Well, I tried to pick up relevant topics, so
Yes,
I think flows are pretty relevant.
Yes, and I'm responsible for flow in my team. Mostly what I wanted to know, which is what I get confused when I'm studying for flow the most, is what is relevant. Like, because you can find algorithms for everything basically. So like, oh, I know like blossom is something I need to study because it has appeared. Now like weighted blossom is something much more complex. I think maybe it's useless to study. Those kind of
For those algorithms,
just like